Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is there. Leave a comment below. It's always fascinating to see how far this little community stretches across the planet. And if you haven't already, consider subscribing so you can drift with us through the vast, strange corners of science and thought. Now, settle in. Let your mind slow down for a moment. Tonight, we're going to talk about something impossibly small. So small, it may be the very foundation of everything we call reality. It's a story about time. Not the time on your clock or the kind that ticks away while you listen, but the smallest possible interval of time that could exist. A moment so brief that our language fails, our mathematics trembles, and our imagination collapses under its scale. Physicists call it Planck Time, the shortest conceivable tick of the universe's clock. But before we get there, let's start with something more familiar. A moment. That's what you're in right now, the present. The elusive sliver of existence that constantly slips between what was and what will be. We live in it, but never quite catch it. By the time you say now, it's already gone, replaced by another now. Humans have always tried to measure this fleeting thing, to cut time into pieces we can count. Once, it was the shadow of a sundial, moving almost imperceptibly across stone. Then came water clocks, sand glasses, pendulums, and the steady beat of mechanical gears. Today, we measure time using the vibrations of cesium atoms. Precisely 9,192,631,770 oscillations per second define what we call 1 second. That's astonishing precision, and yet even this is barely scratching the surface of what nature allows. If we zoomed into smaller and smaller intervals, milliseconds, microseconds, nanoseconds, we'd eventually reach the realm of the ultra-fast, femtoseconds and attoseconds. At these scales, light itself barely has time to move across a few molecules. Lasers can now capture chemical reactions as they happen in trillionths of a second, freezing motion that was once invisible. But all this still belongs to the world of continuity. Smooth, flowing time. The seconds we divide aren't truly discrete. They're just slices of something that seems infinitely divisible, like cutting a thread finer and finer forever. Or maybe not. What if time doesn't flow like water, but clicks like a cosmic metronome, too fast for us to hear? What if there's a smallest beat below which the concept of before and after no longer applies? That's what the idea of Planck time suggests. It's not just another small unit, it's the limit, the edge where our understanding breaks, a boundary drawn not by human technology, but by the universe itself. It's named after Max Planck, the German physicist who, at the dawn of the 20th century, discovered that energy comes in tiny packets, quanta. In 1899, he combined several fundamental constants of nature, the speed of light, the gravitational constant, and his own quantum constant, to define natural Planck units. They weren't meant for daily life. They were meant for a universe stripped of human scales, a reality measured only by the universe's own rules. From these constants, he derived a time scale, about 5.39 times 10 to the negative 44th seconds, a number so small it's hard to grasp what it means. To compare, a single blink lasts about 1/3 of a second. In that time, 10 to the power of 43 Planck moments would have passed. That's a 1 followed by 43 zeros. Even light, the fastest thing in existence, would only travel a single Planck length during that unimaginably brief instant, roughly 1.6 times 10 to the power of minus 35 meters. If you wanted to measure something shorter than that, the mathematics begins to break down. At that scale, the smooth fabric of space and time, which Einstein described in his theory of relativity, stops behaving like a continuous sheet and starts to shimmer with uncertainty. Physicists call this threshold the quantum gravity limit, where quantum mechanics and general relativity collide and both lose their meaning. Think about that. For all our advances, the telescopes that see back to the birth of galaxies, the clocks that lose only a second over the age of the universe, there's a lower bound to time itself, a shortest possible instant, a cosmic frame rate beyond which the film of reality can't be divided. If you tried to look between two Planck times, you wouldn't find a smaller moment hiding there. Time itself, as a meaningful quantity, stops. It's as if reality has pixels, and Planck time marks the smallest temporal pixel that can exist. And yet, this isn't just a curiosity for mathematicians, it's a profound philosophical question. If time is made of discrete quanta, then the flow of time we experience might be an illusion, a smooth performance built from countless invisible instants, the way a movie seems continuous even though it's just a series of still frames. If, on the other hand, time is truly continuous, then Planck time might only represent a limit of our equations, not nature itself, but our current inability to see beyond a certain point. In both cases, we're standing on the same precipice, the point where the known dissolves into the unknown. We can calculate Planck time with breathtaking precision, yet we cannot touch it, measure it, or even properly imagine it. We can say, this is the smallest possible interval, but we can't actually verify it, because any attempt to probe such small durations would require so much energy that we'd collapse space-time itself into a black hole. To observe the smallest moment, we'd destroy the very fabric we're trying to study. So we're left with a paradox. We know the number, we can write it down, but we can never see what it means. That's what makes Planck time so haunting. It's both a discovery and a wall. It tells us where our understanding ends. It whispers that beneath that line, perhaps, time doesn't flow at all. Or maybe it hasn't even begun. In the next part, we'll start to climb that ladder down from the seconds we know, through smaller and smaller intervals, until we reach this mysterious threshold, this smallest possible beat of existence. But for now, as you listen to the quiet hum of your own thoughts, consider this. Every second you experience is built from trillions upon trillions of moments you can never feel, moments that may not even exist in the way we think. And somewhere, between one breath and the next, lies the edge of time itself. Long before anyone dreamed of numbers like 10 to the minus 44, time was something you could see. It was the shadow of a stick on the ground, the movement of the sun across the sky. A simple idea, the passing of light and shadow, day and night. The first humans to measure time didn't think of it as abstract or mathematical. It was woven into survival. When to plant, when to hunt, when the floods would come. The ancient Egyptians used obelisks as giant sundials, marking the shifting length of shadows to divide the day into hours. Those hours weren't all equal, they stretched and shrank with the seasons, but they worked because time back then was about rhythm, not precision. A few thousand years later, in the 14th century, Europe filled with the sound of bells. Mechanical clocks appeared in church towers, great iron machines powered by falling weights. For the first time, time itself became mechanical, no longer a shadow or a song, but a gear that turned at a steady rate. By the 17th century, Galileo noticed something curious. The swing of a pendulum, no matter how wide, always took the same time. That insight became the heart of the pendulum clock, perfected by Christian Huygens in 1656. Its accuracy? A few seconds a day. For the first time, people could coordinate their lives by identical ticks, and yet even that wasn't enough. As science advanced, clocks had to keep pace. The Industrial Revolution demanded precision. The discovery of electricity gave rise to quartz oscillators, the vibrating crystals that beat faster and more consistently than any pendulum could. By the early 20th century, engineers could measure milliseconds, thousandths of a second, and then microseconds, millionths of a second. But something changed when we entered the atomic age. We stopped building clocks out of matter and started building them out of the laws of physics themselves. In 1949, the world's first atomic clock began ticking at the US National Bureau of Standards. It wasn't counting pendulum swings or mechanical vibrations, but the oscillations of microwaves absorbed by ammonia molecules. By 1967, scientists redefined the second entirely. No longer 1/86,400th of a day, but 9,192,631,770 oscillations of the radiation emitted by a cesium-133 atom. It was no longer tied to the rotation of the Earth, which wobbles and slows. It was tied to the unchanging quantum rhythm of the universe. A good cesium clock is so stable that after running for 100 million years, it would be off by less than a second. That's precision bordering on the divine. But of course, scientists didn't stop there. Today, we measure time using optical lattice clocks, instruments so precise they could detect the difference in the flow of time between your head and your feet. That's not an exaggeration. According to Einstein's relativity, time runs infinitesimally faster for your head than your toes, because it's farther from Earth's gravity. In 2022, researchers at the University of Colorado Boulder used an optical lattice clock based on strontium atoms to achieve an uncertainty of 1 second in 15 billion years, longer than the age of the universe. We have reached a point where our measurement of time is limited not by technology, but by fundamental physics. Let's descend the ladder together, from seconds into the abyss of smaller and smaller intervals. A second is what you feel when you count 1, 2. A millisecond, 1,000th of a second, is what separates frames in a fast video or the blink of a digital signal. A microsecond, 1/1,000th, is the world of microprocessors, the heartbeat of modern electronics. A nanosecond, 1/1000th, is the time scale of light travelling just 30 centimetres, about a foot. By the time we reach a picosecond, 10 to the power of -12 seconds, light has barely crossed a human hair's width. Now we enter the truly microscopic frontier, the ultra-fast. A femtosecond is a millionth of a billionth of a second. At this scale, we can watch atoms vibrate within molecules. In 1999, Ahmed Zewail won the Nobel Prize in Chemistry for pioneering femtochemistry, capturing the motion of chemical bonds as they broke and formed. Then came attoseconds, 10 to the -18th seconds. In 2023, Pierre Agostini, Ferenc Krauss and Anne Lhuillier shared the Nobel Prize in Physics for their work in attosecond laser pulses. These pulses are so brief that they can capture the movements of electrons, the fastest processes known in atoms. An attosecond is to a second what a second is to the age of the universe. And still, researchers go further into zeptoseconds, 10 to the -21 seconds, and even yoctoseconds, 10 to the -24 seconds. In 2020, scientists in Hamburg measured a 247 zetosecond delay in how photons interacted with electrons, the shortest time interval ever recorded directly. At these scales, light itself begins to feel sluggish. In a single zeptosecond, it travels less than the width of a hydrogen atom, and yet these intervals, staggering as they are still trillions upon trillions of times longer than the Planck time. Let's pause for a moment to put that into perspective. If a single second were stretched to fill the entire age of the universe, around 13.8 billion years, then a Planck time would be like a fraction of a second within that cosmic timeline, so small that it makes even a zeptosecond look eternal. The Planck time, written as 5.39 times 10 to the -44 seconds, is not just smaller, it's beyond measurement. It's so far down the ladder that the ladder itself stops existing. This isn't hyperbole. If we attempted to observe events that happened on that timescale, we would need energies so immense that the space we're observing would collapse into a black hole. That's because the smaller the time interval you try to measure, the higher the energy you need to resolve it, a consequence of Heisenberg's uncertainty principle. And at 10 to the -44th seconds, that energy becomes so concentrated that it warps space-time itself. It's as if nature has placed a signpost at the bottom of time's staircase. Beyond this point, physics no longer applies. Think of it this way. Imagine you're watching a film. Each frame is a static image, but when projected fast enough, the sequence feels continuous. Now imagine slowing it down. You start to see the individual frames. You could, in principle, slow it forever, until the film becomes a slideshow of still pictures. But Planck Time suggests there's a point where the frames stop being pictures at all, where the film itself ceases to exist. Below this scale, there's no meaningful concept of before or after. This isn't just about instruments or energy, it's about the very nature of reality. The universe may not allow time to exist in smaller pieces because below that threshold, space-time stops being a smooth fabric and starts fluctuating wildly, a storm of quantum uncertainty where geometry itself dissolves. This is what physicists call the quantum gravity regime, the territory where neither general relativity nor quantum mechanics can describe what's happening. When we speak about seconds, milliseconds, and even attoseconds, we're still within the realm of smooth physics, predictable, measurable, continuous. But Planck time lies beyond that horizon. It marks the moment the universe itself was still too young, too dense and too chaotic for any familiar laws to hold. At that scale, it's not just that we can't measure time. Time itself may not exist in any form we recognize. There may be no tick, no flow, no direction, only a quantum haze, an unformed potential from which the very first second, the first something, would eventually emerge. And yet, even though we can't measure or experience a Planck moment, we can calculate it. That's what makes physics such a strange marriage of the imaginable and the incomprehensible. With a few constants, the speed of light, the gravitational constant, and Planck's constant, we can describe the smallest possible sliver of time the universe can support. It's a triumph of logic built on the edge of mystery. We know the number, but not what it means. It's like having the coordinates of a place you can never visit. The ladder of time, from seconds to Planck time, is more than just a sequence of shrinking numbers. It's a map of human curiosity. From the shadow on a wall to the oscillations of atoms, every new step downward has revealed a new world, and then shown us how much further there is to fall. At the bottom lies the Planck frontier, a threshold not just of technology, but of existence itself. In the next part, we'll meet the man who gave his name to this scale, Max Planck, the quiet German physicist who unknowingly opened the door to quantum theory, and with it, to the smallest slice of time that can ever be. At the end of the 19th century, physics felt complete. Scientists believed they had almost decoded the entire machinery of nature. Newton's laws described the motion of planets and apples. Maxwell's equations united electricity, magnetism, and light. Thermodynamics explained the flow of heat and energy. To many physicists of the time, the universe seemed like a grand clock. Precise, elegant, predictable. And then came a quiet, disciplined German physicist named Max Carl Ernst Ludwig Planck. Born in 1858 in the city of Kiel, he was not a revolutionary by temperament. He was meticulous, introverted, and deeply respectful of tradition. He never set out to overturn the world, only to understand it more perfectly. He once wrote that a new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die. He knew that progress often moved slower than discovery. In the late 1890s, Planck was studying something deceptively simple, how objects glow when they're heated. If you've ever watched metal in a forge, you've seen it, first red, then orange, then white hot. Physicists called this phenomenon black-body radiation, and it was one of the biggest unsolved puzzles of the time. According to the equations of classical physics, a hot object should emit infinite energy at short wavelengths, a paradox called the ultraviolet catastrophe. Clearly, that wasn't happening in reality, but the mathematics refused to cooperate. Planck tried every conventional approach he could think of, adjusting constants, tweaking formulas, and re-deriving the old equations. Nothing fit the data. Finally, almost in desperation, he tried something no one else dared. What if energy didn't flow smoothly like water, but came in tiny packets? What if nature itself was quantized? built not from continuous waves, but from discrete steps. So he introduced a new idea. Energy could only exist in multiples of a small, indivisible unit. He called that unit h, now known as Planck's constant. He expressed it through a simple relation, energy equals h times frequency. In other words, the energy of a particle of light, a photon, depends directly on how quickly it vibrates. At the time, this was heresy. No one believed energy could come in chunks. Planck himself didn't fully believe it. He described his own idea as an act of desperation. But it worked. The new formula matched experimental data perfectly. That one equation, energy equals h multiplied by frequency, quietly lit the fuse of the quantum revolution. Afterward, Planck grew fascinated with the deeper meaning of his constant. He began to suspect it was not just a mathematical fix, but a window into nature's most fundamental design. He wondered, could there be natural units of measurement, units not defined by human inventions like seconds or meters, but by the universe itself? So he took the three most fundamental constants known to physics. The gravitational constant, often written as g, which sets the strength of gravity. The speed of light, written as c, the ultimate speed limit of the cosmos. And his own quantum constant, written as h bar, meaning h divided by 2 times pi, which defines the granularity of quantum action. Then, through dimensional reasoning, a kind of mathematical alchemy, he combined these constants to see what fundamental scales of nature might emerge. The results were astonishing. From those three constants, Planck derived three natural units. A Planck length of approximately 1.616 times 10 to the power of minus 35 meters. A Planck time of about 5.39 times 10 to the power of minus 44 seconds. And a Planck mass of roughly 2.18 times 10 to the power of minus 8 kilograms. About the weight of a flea's egg, yet holding the energy of a small nuclear explosion. These weren't arbitrary numbers. They weren't tied to any physical artifact or astronomical cycle. They were universal, constants that would hold true anywhere in the cosmos, for any civilization, human or otherwise. In a 1900 lecture to the German Physical Society, Planck said, "These natural units will retain their significance for all times and for all civilizations, even extraterrestrial and non-human ones." He was right. 100 years later, those same constants still define the edges of our understanding. What Planck had done was conceptually radical. Until then, humanity measured reality using human standards, the meter based on the Earth's size, the second based on its rotation, the kilogram defined by a lump of platinum iridium stored in Paris. Planck abandoned all of that. His system didn't depend on Earth or even on matter. If every planet and every atom vanished, the ratios between those constants would still be true. He had found what might be called the universe's own language, a built-in scale system that existed long before humans started measuring things. An alien physicist working on the far side of the universe would eventually find the same values, the same g, the same c, the same h bar, because they are not human inventions. They are woven into the structure of reality itself. The numbers themselves are almost incomprehensible. A Planck length, 1.616 times 10 to the power of minus 35 meters, is so small that if an atom were stretched to the size of the observable universe, a Planck length would be smaller than a single leaf inside it. A Planck time, 5.39 times 10 to the power of minus 44 seconds, is the time light takes to cross that distance. And the Planck mass, though tiny by everyday standards, is colossal compared to the masses of subatomic particles. Together, these numbers define a realm where our current theories, relativity and quantum mechanics, collide and blur. It's the domain where gravity becomes as strong as quantum effects, and where space-time itself might disintegrate into something unrecognizable. When Planck first introduced these units in 1899, few took notice. To his peers, they were little more than a curiosity, mathematically elegant, but far removed from any possible experiment. At that time, the smallest measurable distances were around 1 × 10 to the power of -10 meters, the scale of atoms. Planck's numbers were 25 orders of magnitude smaller. To visualize the difference, if a single atom were expanded to the size of our Milky Way galaxy, a Planck length would still be smaller than a single snowflake floating between its stars. It was the first glimpse into the unfathomably small. But what Planck truly discovered wasn't just a set of numbers, it was a principle. He revealed that nature itself has boundaries. There are limits beyond which our familiar laws cannot be stretched. The constants he used, G, C, and H bar, represent 3 distinct realms of physics. G, the constant of gravity, governs the structure of space and the motion of stars and planets. C, the speed of light, links space and time in Einstein's relativity. H bar, the reduced Planck constant, determines the quantum of action, the smallest step in the dance of energy and matter. Each of these constants rules its own kingdom, but when you combine them, you reach the intersection of all kingdoms, the Planck scale. At that frontier, the very notions of distance and duration begin to dissolve. It's where space, time, and energy are inseparably fused. It's fascinating that Planck himself wasn't a revolutionary like Einstein or Bohr. He was a reluctant founder of a revolution he never intended to start. When the younger physicists embraced the wild implications of quantum mechanics, uncertainty, wave-particle duality, and probabilistic reality, Planck was skeptical. He admired their work, but found it philosophically disturbing. He preferred order, determinism, cause and effect, and yet his constant, his little h, was the key that unlocked the entire quantum world. Einstein would later say, "The father of quantum theory is Planck, whose fame will be immortal." And so it was. There's a subtle beauty in what Planck uncovered. He showed that the universe isn't infinitely divisible or scale-free. It has proportions, a built-in rhythm of its own. We measure the world with clocks and rulers of our own making. Planck discovered that the universe measures itself. His constants are like cosmic DNA, the same pattern written everywhere, from the first moments after the Big Bang to the quantum fluctuations beneath your fingertips. They tell us that physics is not arbitrary. It is sculpted by the universe's own internal logic. And through those constants, Planck glimpsed something eternal, a harmony that binds the vast and the minute, the continuous and the discrete. When we talk about Planck time today, that infinitesimal 5.39 × 10 to the power of -44 seconds, we're speaking the language he invented, a universal metric that defines the border between what can be known and what cannot. The Planck era, the universe's first instant after the Big Bang, lasted exactly 1 Planck time. During that moment, everything we now understand, space, energy, gravity, and matter, was compressed into one indistinguishable unity. Planck's numbers describe that boundary, the dawn of physics itself. It's humbling to realize that a man working by candlelight in 1899, with pen, paper, and persistence, could define the scales that describe the birth of the universe. Max Planck didn't just give us equations, he gave us perspective. He showed that reality comes with its own measures, built-in, eternal, and unchanging, and that we, for all our fleeting moments, are creatures living inside those constants. In the next part, we'll explore what Planck time itself actually represents, not as a number, but as a concept. We'll follow light across the tiniest imaginable distance and see why, beyond that, even the idea of time begins to lose its meaning. At the heart of every mystery in physics lies a number that seems almost innocent until you realize what it means. Planck time is one of those numbers. It's defined as the time it takes for light, the fastest thing in existence, to travel a distance equal to 1 Planck length. That's about 1.616 times 10 to the power of -35 meters. And since light moves roughly 300 million meters per second, when you divide that distance by that speed, you get an answer so tiny it almost stops existing, 5.39 times 10 to the power of -44 seconds. That's Planck time, the shortest possible duration the universe allows. It's not just small, it's beyond small. It's the edge of time itself. Let's try, futilely, to imagine it. Start with a second, the unit you know. Divide it into 1,000 parts and you have milliseconds. Divide again by 1,000 microseconds, again nanoseconds. You're now in the realm of light pulses and digital circuits. Go smaller still. Picoseconds, femtoseconds, attoseconds. These are the scales of chemistry and electron motion, the frontiers where human instruments can just barely reach. Now imagine you shrink an attosecond, which is 1 times 10 to the power of minus 18 seconds, by another 26 orders of magnitude. That's 1,000,000 trillion times shorter. That's a Planck time. If the entire age of the universe, all 13.8 billion years, were compressed into a single second, a Planck time would be to that second what a single heartbeat is to a span of 10 trillion universes. It is to time what a single atom is to the cosmos, and then some. At such scales, our familiar reality evaporates. Space and time, which seems smooth and continuous to us, begin to shimmer and distort. Einstein's equations no longer behave. In general relativity, space-time is like a flexible fabric, curved by mass and energy. In quantum mechanics, energy comes in discrete quanta, never continuous. At the Planck scale, these two descriptions collide. When physicists try to apply both theories at once, quantum rules on the fabric of space-time, the math explodes, literally. Equations that once described stars and particles now yield infinities, meaningless, self-contradictory results. The two pillars of modern physics, relativity and quantum mechanics, tear each other apart. This is why the Planck scale, and especially Planck time, represents a boundary. It's not a line we've crossed, but one we can't cross without rewriting the laws of nature. To understand why, picture a photon of light, the universe's speed champion, even at its fastest. In the time of 1 Planck moment, it travels only a Planck length, about 1.6 times 10 to the power of minus 35 meters. That distance is so absurdly small it makes a proton, with a diameter of about 1.6 times 10 to the power of minus 15 meters, look like a galaxy. In fact, a proton is 20 powers of 10 larger than the Planck length. That means you could line up 10 quintillion Planck lengths, that's 10 billion billion, just to stretch across a single proton. Try to imagine zooming in further than the proton, past the quarks, past the gluon fields, deeper into nothingness. Eventually, you'd reach a scale so fine that position and distance stop being meaningful. The geometry of space itself begins to fluctuate, twisting, bubbling, boiling. Physicist John Wheeler called this strange, foamy realm quantum foam. At this level, space-time isn't a smooth fabric. It's more like a sea of frothing energy, constantly flickering in and out of existence. And this turbulence isn't a metaphor. It's a literal consequence of quantum uncertainty. According to the uncertainty principle, the more precisely you try to measure something, the more uncertain its complementary quantity becomes. If you try to pinpoint a particle's location with extreme accuracy, its momentum becomes wildly uncertain, and vice versa. Now, imagine applying that principle to space-time itself. At the Planck scale, any attempt to measure the position or curvature of space-time injects so much energy into that region that it collapses under its own gravity, forming a miniature black hole. In other words, to see the Planck realm is to destroy it. The act of measurement erases the thing you're trying to measure. This is not a technological limitation, it's a fundamental one. The laws of physics themselves prevent us from probing below Planck time or Planck length, because at those scales, space-time loses its identity. You might wonder, what does loses its identity mean? In everyday physics, we can describe the universe as a smooth continuum, an infinite grid of coordinates. But at the Planck scale, that grid dissolves. Time no longer flows like a river. It behaves more like the ticking of an invisible clock, or perhaps even worse. It stops being a process altogether. Some physicists believe that below Planck time, the concept of before and after simply doesn't exist. That's because causality, the idea that one event leads to another, requires time intervals large enough for cause and effect to be distinct. At 10 to the minus 44th seconds, those distinctions blur. Events might not have an order. The universe, in that first moment, may not have happened in any temporal sense we can understand. This isn't just theoretical musing. The earliest phase of the Big Bang, known as the Planck era, occurred within the first few Planck times of existence. Before that, the universe was so dense, so hot, and so quantum chaotic that space-time itself was undefined. There was no space expanding and no time ticking. Only an indescribable pre-physical state of potential. After roughly one Planck time, the universe cooled enough for space-time to solidify into something resembling a continuous field. That's when Einstein's equations begin to apply. So when we talk about the Big Bang, we're really talking about the moment after the Planck era, the moment when time, in a meaningful sense, began. This leads to an astonishing idea. The universe might have a smallest possible moment of existence. You can divide a second into smaller and smaller pieces, but you can't go below the Planck threshold. Not because we lack technology, but because time itself has no structure below that limit. If time were a film, the Planck time would be the duration of a single frame. You can't project the movie faster, you'd only repeat the same frame. So, just as matter seems to be made of discrete atoms, time itself might be composed of discrete moments, indivisible, universal quanta. This idea challenges everything we take for granted. In classical physics, the universe is continuous, smooth, and infinitely divisible. But the quantum world seems to say, no. There's a smallest possible scale. Beyond this, reality has no meaning. Think about it. Between one Planck moment and the next, the entire universe could change configuration. And yet, to us, it appears continuous. Just as a movie feels smooth, even though it's made of still frames, our perception of time may be built from countless Planck-sized ticks that we can never detect individually. Some theories go even further. They suggest that time isn't just quantized, it's emergent. That means time might not be a fundamental ingredient of the universe at all, but something that appears only when particles interact in certain ways. Below the Planck scale, there might not be a ticking clock, just relationships between quantum events from which time is born as a kind of illusion. If that's true, then Planck time marks not only a physical boundary, but a philosophical one. It's the line between something and nothing, between existence and possibility. It's where Einstein's smooth space-time yields to the granular chaos of the quantum. It's where gravity, geometry, energy, and time all merge into a single, unified reality that we still don't understand. Physicists have spent decades trying to bridge this gap, to find a theory that unites the large and the small, the continuous and the discrete. They call it quantum gravity, but no one yet knows exactly what form it takes. Some believe it will come from string theory, where the tiniest particles are vibrating strings existing in multiple dimensions. Others favour loop quantum gravity, which imagines space-time itself woven from tiny loops of finite size. Whatever the answer, all of them agree on one thing. Planck time marks the border of knowable reality. It's the fence line of the cosmos. So when we speak of Planck time, those 5.39 times 10 to the power of minus 44 seconds, we're really speaking of the threshold between order and mystery. It's the smallest heartbeat the universe has ever known. Below that, there's no rhythm, no melody, only silence. Not because nothing happens, but because happening itself stops making sense. It's humbling, almost frightening, to realize that everything we've ever experienced, from the spin of galaxies to the blink of an eye, unfolds in an endless chain of these unimaginably brief intervals. Every moment of our lives, every thought, every flicker of light is built from countless Planck moments stacked together, invisible and indivisible. They are the pixels of time, and we are the stories they compose. In the next part, we'll dive deeper into what might be happening inside that smallest instant, the chaotic foam of space-time itself. A world where geometry wobbles, where distances fluctuate, and where the universe's very fabric trembles with quantum uncertainty. The realm known as quantum foam, the place where space-time stops being calm and begins to boil. At the human scale, the universe seems stable. The ground beneath your feet feels solid. The space between stars seems empty and silent. Even the flow of time feels smooth, a quiet current moving in one direction, never rippling, never disturbed. But physics teaches us that this calmness is an illusion of scale. Just as a still pond reveals tiny waves when seen up close, the universe itself begins to shimmer when viewed under the microscope of fundamental physics. If we could somehow zoom in, far beyond the atom, beyond the proton, beyond the very limits of what space and time can be, we would discover that the cosmic fabric is not smooth at all. It's alive with motion, flickering, foaming, unstable, a restless sea of uncertainty. Physicist John Archibald Wheeler had a name for this hidden turbulence. In 1955, he called it quantum foam. Wheeler was one of the most imaginative minds of the 20th century, a man who saw the universe as both a grand machine and a living thought experiment. He coined the term black hole, mentored Richard Feynman, and loved to ask questions that made even Einstein pause. By the mid-1950s, physicists were beginning to understand that quantum mechanics, the theory governing the very small, and general relativity, the theory governing the very large, were incompatible. Each worked perfectly within its own domain, yet when combined, they produced chaos. Wheeler tried to imagine what space-time itself might look like at the Planck scale, around 1.6 times 10 to the power of minus 35 meters, and he realized it could not be smooth. At that scale, the Heisenberg uncertainty principle, one of the cornerstones of quantum theory, dominates everything. The principle says in essence that you can never know both the exact position and exact momentum of a particle at the same time. The more precisely you measure one, the more uncertain the other becomes. But this rule doesn't just apply to particles, it applies to energy. And through Einstein's equation, energy equals mass times the speed of light squared. It applies to the curvature of space-time itself. So if energy fluctuates, then space-time, which bends in response to energy, must fluctuate too. The result? Space-time can never remain perfectly smooth. Imagine a calm sheet of fabric stretched across a table. That's the space-time of general relativity. Elegant, continuous, unbroken. Now imagine dropping countless microscopic grains of sand onto it, each representing quantum uncertainty. The surface would begin to jitter, dip, and tremble. That's the space-time of quantum mechanics. Not flat, but quivering with energy. At the Planck scale, those ripples become so extreme that the geometry of space and time itself starts to fluctuate violently. Distances shrink and stretch unpredictably. Tiny regions appear and vanish. Space twists into itself, forming fleeting tunnels, miniature wormholes that blink in and out of existence faster than the blink of a Planck moment, 5.39 times 10 to the power of minus 44 seconds. This chaotic, bubbling picture is Wheeler's quantum foam. It's not a metaphor, it's a literal, physical description of what happens when we push our theories to their limits. At such scales, energy density becomes enormous. The vacuum, what we call empty space, seethes with activity. Particles and antiparticles spontaneously appear and annihilate, borrowing energy from nothing and returning it almost instantly. Even the speed of light, constant in classical physics, becomes an average value across a wildly fluctuating geometry. Space and time lose their meaning as continuous quantities. They become statistical, probabilistic, like everything else in the quantum world. The quantum foam is more than chaos. It's the foundation from which order emerges. In Wheeler's vision, this violent sea of microstructure could be the raw material from which the universe itself was sculpted. In the earliest moments after the Big Bang, during that first Planck time, space-time may have been nothing but this frothing quantum soup. Tiny fluctuations within it, amplified by inflation, could have grown into the large-scale structures we see today. Galaxies, clusters, filaments of dark matter stretching across billions of light years. It's astonishing to think that everything, stars, planets, even us, might trace its origin back to jittering imperfections in the geometry of the primordial foam. The universe, in that sense, is a ripple frozen into cosmic history, a fossil of quantum noise. The mathematics behind this picture is staggering, but the principle is simple. At the Planck scale, quantum effects dominate gravity. You can no longer treat space-time as a smooth fabric. It becomes granular, with energy fluctuations bending it wildly. These fluctuations cause local distortions in curvature, tiny ephemeral wrinkles. They may even connect distant points of space-time briefly, forming microscopic wormholes, handles, in the geometry that open and close too quickly for anything to pass through. Wheeler once described this as space-time frothing like a pot of boiling water. Each bubble in that pot was a momentary distortion of geometry, a little quantum whirlpool of reality itself. And while these bubbles are unimaginably small and transient, they might have consequences we can still observe today. For instance, modern cosmology tells us that the early universe wasn't perfectly uniform. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see tiny variations in temperature, parts of the sky just a few millionths of a degree warmer or cooler than others. Those fluctuations are believed to be the fingerprints of quantum foam, the first imprints of randomness magnified to cosmic scale. What began as subatomic jitter became the scaffolding for galaxies. The foam at the base of reality might be the artist that painted the structure of the cosmos. It's strange, even poetic, that uncertainty could be the architect of everything. We often think of order emerging from control, but the universe seems to thrive on the opposite. It builds galaxies from fluctuations, life from chaos, time from statistical averages. If space-time were perfectly smooth, if no foam existed, the cosmos might have remained featureless and static. Instead, it dances because of its imperfections. Quantum foam is a reminder that creation may depend on instability, that the trembling of space-time at its smallest scales was not noise, but the overture to the cosmic symphony. Wheeler's idea inspired generations of physicists to seek a deeper understanding of what space and time truly are. His students and colleagues carried the torch forward. Richard Feynman developed the path-integral approach to quantum mechanics, where every possible history of the universe contributes to its behaviour. Bryce DeWitt worked with Wheeler to formulate the Wheeler-DeWitt equation, an attempt to describe the entire universe as a quantum wave function. That equation, curiously, contains no time variable at all. Time, in that formulation, is not fundamental. It emerges from relationships between states of the universe. In other words, time may rise out of the foam. Quantum foam also underlies many of today's leading theories of quantum gravity. In string theory, the foam is replaced by vibrating strings or membranes whose quantum fluctuations give rise to space-time itself. In loop quantum gravity, the foam becomes a network of loops, a web of finite quantum links defining space at the smallest possible scale. In both views, the smoothness of space is an illusion born from countless microscopic quanta of geometry, even in emerging digital physics, where the universe is seen as information. The foam becomes the lowest level code of reality, the smallest computational bit of space-time. No matter the approach, one truth seems universal. The universe is not built from matter resting in empty space. Rather, space itself is an active, fluctuating entity, a restless sea whose vibrations create the illusion of stability. If we could somehow witness it, quantum foam would be an astonishing sight. Imagine standing at the edge of nothing, watching space-time flicker like static on an infinite screen, tiny bubbles of geometry inflating and collapsing faster than any clock could ever tick. Each one a possible universe, a possible path, appearing and vanishing within 10 to the power of minus 44 seconds. To us, such a realm is forever hidden, not because it's far away, but because it's beneath reality itself. It's not another layer of matter waiting to be seen under a better microscope. It's the limit of definition. Below that foam, there may be no below. Yet from that chaos emerged the cosmos we inhabit. From the wild boiling of Planck-scale space came the order of galaxies and gravity, of stars and consciousness. Every atom in your body is, in a sense, a ripple of that ancient foam, stretched and cooled across billions of years. When you look at the night sky, at the calm, star-filled silence, remember, what you see as stillness is the slow unfolding of a foam that never stopped vibrating. The universe did not leave its quantum roots behind. It carries them in every fluctuation, every wave, every photon of light that reaches your eyes. And so, the quantum foam is not just a scientific concept, it's a reminder of our origins. We are beings made of space-time's vibrations, descendants of uncertainty, children of a trembling universe that never truly rests. Every second, we live suspended between those Planck-sized ripples, floating atop the most restless surface imaginable, the quantum sea that gave birth to everything. In the next part, we'll travel back to the beginning, to the moment when this foam first ignited. We'll explore the Planck era, the first 10 to the power of minus 43 seconds after the Big Bang, when energy, gravity, and quantum mechanics were one, and time itself was just beginning to take shape. To imagine the beginning of everything, you have to start where imagination itself begins to fail. The Planck era, the first 10 to the power of minus 43 seconds after the Big Bang, is the ultimate frontier of knowledge. It's not just the beginning of the universe as we know it, it's the boundary between what can be known and what lies forever beyond human comprehension. If you could rewind the cosmic clock, past the birth of galaxies, past the formation of atoms, even past the first photons of light, you would reach a point where the universe was smaller than a subatomic particle, yet contained everything that would ever exist. In that first moment, there were no stars, no space, no matter, and possibly no time in the sense we understand it. There was only a storm of unimaginable density and heat, a reality so extreme that the very fabric of space-time itself was unstable. Physicists call this the Planck era, and it lasted only for about 5.39 times 10 to the power of minus 44 seconds, the smallest measurable slice of time, the Planck Time. Within that instant, the universe existed as pure energy. Temperatures reached roughly 10 to the power of 32 Kelvin. That's 100 million trillion degrees, far beyond anything that can ever be replicated in a laboratory. At those temperatures, no known form of matter can exist. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, had not yet separated. They were merged into a single unified interaction, a kind of primal force that would later fracture into the familiar ones as the universe expanded and cooled. In this primordial state, all distinctions blurred. There were no particles because particles require space to exist in. There was no light because photons require space-time to travel through. There were no atoms because even the concept of distance had no meaning. All that existed was quantum chaos, a dense, flickering foam of energy where space-time itself was uncertain. To say the universe was hot at this stage is almost misleading, because temperature assumes you can define energy per particle, and at that moment there were no distinct particles to measure. It was an undifferentiated ocean of possibility, an everything and nothing state. If you could somehow have witnessed it, you wouldn't have seen light or matter or even darkness. You would have seen a universe that hadn't yet learned to exist, a realm of violent uncertainty where the laws of physics as we know them had not yet emerged. At these scales, the quantum and the gravitational are locked in a constant struggle. Quantum mechanics tells us that energy fluctuates, uncertainty reigns, and nothing is perfectly defined. General relativity tells us that energy shapes space-time. It curves it, warps it, defines the geometry of the universe. But what happens when the amount of energy is so high that it curves space-time into a singularity, and that very curvature is subject to quantum uncertainty? At that point, both theories collapse. Their mathematics, elegant and precise in their own domains, explode into infinities when applied together. This is the paradox of the Planck era, the moment where our best theories of the universe stop working. To make sense of it, physicists have tried to reconstruct what this instant might have been like using what fragments of theory still hold. We know that the total energy of the universe then was not infinite. It was simply confined to an unimaginably small space. The energy density was on the order of 10 to the power of 94 grams per cubic centimetre, so high that even the concept of a point loses meaning. If you could somehow take all the energy in the visible universe today and compress it back to that moment, it would occupy a region smaller than a single Planck length, 1.6 times 10 to the power of minus 35 metres. At that density, gravity becomes as strong as the other fundamental forces. There is no separation between what bends space and what fills it. Space and time themselves are quantum objects, flickering in and out of definition. The idea that space and time might not have existed yet is not poetic exaggeration, it's a literal statement of physics. The concept of before the Planck era is meaningless, because time itself is part of what was being created. To ask what happened before the Big Bang is like asking what's north of the North Pole. The question dissolves at the edge of definition. In this sense, the Planck era was not just the first moment after creation, it was creation. It was the phase in which the rules of existence were being written. The constants that govern everything, the speed of light, the strength of gravity, the charge of the electron, were being set like tuning knobs on a cosmic instrument. Had they been tuned even slightly differently, the universe that followed might have collapsed instantly, or expanded too fast for galaxies to form. In that brief, furious instant, the conditions for everything that would ever exist were decided. The transition out of the Planck era, when the universe cooled and expanded just enough for space-time to stabilize, marks the birth of the grand unified era. That's when the first separation occurred. Gravity broke away from the other forces, becoming its own distinct phenomenon. With that single fracture, the universe began to unfold structure. Time started to flow in a meaningful way, rather than flicker chaotically. Space acquired a measurable geometry, and with the cooling that followed, energy could condense into particles, light, and the seeds of matter. But at the Planck scale, even the notion of geometry was probabilistic. Distances didn't have fixed values, curvature fluctuated wildly from point to point. It was, in every sense, a foaming storm of quantum geometry, the raw origin of everything we now perceive as smooth and continuous. If you could zoom into a single Planck volume, that is, a cube of space with each side measuring 1 Planck length, it would not look like emptiness. It would look like a flickering network of possibilities, space-time itself fluctuating, collapsing, reforming and vanishing in rapid succession. Each moment, each fluctuation might have contained the potential for entire universes, though only one of them, ours, continued to expand. This is why scientists often describe the Planck era as unknowable. It's not just that our telescopes can't see it. It's that our physics cannot describe it. We can trace the history of the universe all the way back to roughly 10 to the power of minus 35 seconds after the Big Bang, but the first 10 to the power of minus 43 seconds remain forever hidden behind the horizon of theory. Even the cosmic microwave background, the oldest light we can observe, was emitted roughly 380,000 years later. The Planck era is far beyond any direct evidence, locked in the unreachable past. Yet, curiously, it may still echo in the structure of reality itself. The fluctuations that existed in that chaotic phase, the foam of spacetime, the ripples of quantum uncertainty, might have left subtle fingerprints in the cosmic fabric. The very unevenness of matter, the slight variations that allowed galaxies to form, could all trace their origin to the random tremors of the Planck era. And so, even though we cannot see it, we can feel its consequences in every atom that exists. The order we inhabit was born from disorder. The predictability of physics today was forged from the collapse of predictability at the dawn of time. That paradox, that chaos gave birth to law, lies at the core of modern cosmology. It reminds us that the universe is not static or eternal, but dynamic, self-creating, and deeply strange. Some theories suggest that our universe is not the only one to have emerged from that primordial foam. The Planck era, they say, may have spawned countless bubble universes, each with its own physical constants and laws. We may be living in one bubble among many, adrift in a multiverse born from fluctuations too brief for time to measure. If that's true, then what we call the beginning may have been just one of many beginnings, the crest of a wave in an infinite sea of potential. But even without those speculations, the Planck era stands as the most mysterious chapter in the history of existence. It is the point where our understanding of nature collapses, not because we lack imagination, but because reality itself may not have been fully formed. Beyond that threshold, the universe may not have been a thing at all, but a question waiting to be asked. And when it was, when space-time stabilized, when gravity split from the other forces, when energy began to flow and organize, that question became an answer. That answer became the cosmos. And within that cosmos, billions of years later, arose beings capable of looking back and wondering what that first instant might have felt like. The Planck era was not simply a beginning, it was the moment reality learned to exist. For over a century, physics has lived with a quiet contradiction, one so deep that it cuts through the foundations of science itself. On one side stands Einstein's general relativity, the grand theory of the cosmos, smooth, geometric, continuous. It tells us that gravity is the curvature of space-time, that planets follow paths bent by the shape of the universe itself. On the other side stands quantum mechanics, the theory of the microscopic world, chaotic, statistical, discrete. It describes a universe of probabilities and flickering fields, where uncertainty is fundamental and nothing exists until it's measured. Each theory is brilliant, each is experimentally flawless, and yet they cannot coexist. When you bring quantum mechanics into the heart of a black hole, or try to describe the first instant of the Big Bang, relativity and quantum physics clash violently. The equations break, infinities appear. Reality, as we describe it, falls apart. Physicists have spent decades trying to fix this fracture, to build a theory that unites the laws of the large and the laws of the small. This pursuit is often called quantum gravity, the search for a single framework that describes how space-time behaves when it's both curved by gravity and fluctuating quantumly at the Planck scale. No one has found the final answer yet, but several contenders have risen from the chaos. Among them, two stand out: string theory and loop quantum gravity. String theory began with a beautiful idea. Perhaps the building blocks of reality aren't point-like particles at all, but tiny vibrating strings of energy. In this picture, everything, electrons, quarks, photons, even gravity itself, emerges from the vibrations of these infinitesimal strings. Just as a violin string can produce many notes depending on how it vibrates, the universe's fundamental strings produce different particles depending on their modes of vibration. An electron might be a string vibrating one way. A graviton, the hypothetical quantum of gravity, might be the same string vibrating another way. In this view, all of nature's diversity arises from rhythm, a cosmic symphony played on strings smaller than any known distance, roughly the Planck length of 1.6 times 10 to the power of minus 35 meters. The mathematics of string theory is stunningly rich. It naturally incorporates quantum mechanics, includes gravity, and predicts the existence of particles that behave exactly as we'd expect from known physics. But there's a catch. The equations only make sense if the universe has more dimensions than the 4 we experience. According to string theory, reality might have 10 or even 11 dimensions, with 6 or 7 of them curled up so tightly at the Planck scale that we can't perceive them. Imagine an ant walking on a telephone wire. To the ant, the wire is a wide, 2-dimensional surface. It can move forward or backward and around the circumference. To us, from afar, the wire looks like a one-dimensional line. In the same way, these hidden dimensions of the universe might be coiled up on scales too tiny for any observation to detect. In the 1990s, physicists discovered something remarkable inside string theory. It wasn't just one theory, but a family of them, all connected by subtle symmetries. These variations merged into a broader framework known as M-theory, which suggests that strings might not be one-dimensional at all, but tiny vibrating membranes, or brains, existing in higher dimensions. According to this view, our entire universe might be a 3-dimensional brain floating in a higher dimensional space. Gravity, unlike the other forces, could leak into those hidden dimensions, explaining why it seems so weak compared to electromagnetism or the nuclear forces. If true, this would mean that the Planck scale, that tiny, unreachable domain, might be connected to vast extra dimensions beyond our perception. The smallest scales could hold the key to the largest structures imaginable. But not everyone is convinced by strings and hidden dimensions. Another approach, entirely different in philosophy, is loop quantum gravity. Where string theory begins with assumptions about new dimensions and objects, loop quantum gravity starts from something simpler, Einstein's equations themselves, and tries to quantize spacetime directly. The central idea is breathtaking in its simplicity. Space is not continuous. It's woven. Like fabric made of threads, space-time is built from discrete, finite loops. In this theory, the geometry of the universe is composed of minuscule loops of energy, interlinked in a vast network known as a spin network. Each loop represents the smallest possible unit of area or volume, measured in multiples of the Planck length and Planck volume. If you zoomed in far enough, you wouldn't find a smooth surface of space. You'd find a tangled web, an intricate mesh of quantum geometry. Space itself would look granular, like the digital pixels of a cosmic simulation. These loops are not embedded in space, they are space. Space-time, in this view, emerges from the connections between them, the way a picture emerges from the pixels on a screen. Time, too, is not continuous. It ticks forward as these loops evolve and rearrange. This is one of the most profound consequences of loop quantum gravity. Time is not a background stage on which events unfold. It's an emergent property of how space-time itself changes at the smallest scale. In that sense, time might not exist independently at all. It's a byproduct of information flowing through the network of the universe. There are other, equally daring ideas orbiting this mystery. Some physicists have proposed that space-time is fundamentally digital, that reality is made not of fields or waves, but of information itself. In causal set theory, the universe is described as a vast collection of discrete events linked by cause and effect, like a growing web of who happened before whom. There's no continuous timeline, no background grid, only a network of relationships. Each new event that occurs adds a new node to the structure, expanding the universe one tick of causality at a time. In this view, time doesn't flow like a river, it accumulates like a chain of data. The universe, then, is not a continuous film, but a collection of frames stitched together by cause. And in digital physics, a concept championed by thinkers like John Archibald Wheeler and Edward Fredkin, the universe itself might be a vast computation. Wheeler called it the it from bit idea, meaning that everything physical arises from information. In other words, reality is not built from matter, but from yes or no choices, bits of information, the most fundamental currency of existence. From that perspective, the Planck scale isn't just a physical limit, it's the smallest possible unit of information processing in the universe. The cosmos could be a self-simulating system, updating its own state in Planck-sized ticks, like a cosmic computer running at the ultimate frame rate. Each of these theories, strings, loops, causal sets, and digital universes, offers a different way to think about what lies beyond the barrier of Planck time. They all share one belief, that the smooth spacetime of Einstein's relativity is an illusion, a large-scale average of something deeper, discrete, and quantum. But how do we test any of this? The Planck scale is so far beyond our reach that no microscope, no collider, no instrument can probe it directly. Even the Large Hadron Collider, humanity's most powerful machine, reaches energies trillions of times too low to disturb space-time at that level. So physicists have turned to indirect evidence, subtle signs that might hint at quantum gravity's fingerprint. They search the afterglow of the Big Bang, the cosmic microwave background, for minute distortions that could have been imprinted by quantum fluctuations during the universe's earliest moments. They examine the polarization of light from distant galaxies, hoping to detect tiny deviations caused by spacetime's granular structure. They study gravitational waves from colliding black holes, looking for echoes or dispersion that shouldn't exist if spacetime were perfectly smooth. So far, the universe has kept its secrets, but even null results, the absence of evidence, have guided the search, helping physicists rule out models and refine their understanding of what the quantum fabric of reality might be. What makes this quest extraordinary is not just the math or the complexity, it's the philosophy behind it. To build a theory of quantum gravity is to ask the most fundamental question imaginable. What is reality made of? Is space a thing, or just a relationship between things? Is time an illusion, or a process emerging from deeper order? Are we living in a universe that is continuous, or one that flickers, pixel by pixel, moment by moment, beneath our perception? We don't yet know, but in every attempt to answer, whether through strings vibrating in 10 dimensions or loops spinning in quantum webs, we're forced to confront something profound. The universe seems to value both chaos and order, both granularity and flow. It may be that at the smallest scales, reality dances between those opposites, weaving continuity from discreteness, creating time from timelessness, and transforming uncertainty into the structure we call existence. Perhaps, in the end, that's what the Planck scale really represents. Not a wall blocking our knowledge, but a mirror reflecting our curiosity. A reminder that beyond the barrier of what we can measure, the universe still hums with possibilities, each theory another vibration in the cosmic symphony of understanding. Humanity has always measured the world to understand it. We've built clocks that can keep time so precisely they would lose less than a second over the lifetime of the universe. We've mapped atoms, recorded electrons in motion, and timed events lasting less than a billionth of a second. And yet, when it comes to Planck time, 5.39 times 10 to the power of minus 44 seconds, we face a barrier unlike any other. It isn't just difficult to measure, it's fundamentally impossible. To grasp why, it helps to remember how we measure time in the first place. Every clock, from a pendulum to an atomic standard, relies on repetition, on something oscillating at a known frequency. An old grandfather clock uses the swing of a pendulum. A quartz watch uses the vibration of a crystal. An atomic clock measures the energy transitions in atoms. But each of these has a limit. You can only count intervals as short as the system you're using can repeat. If we wanted to build a clock capable of measuring Planck scale intervals, we'd need a process that could tick 10 to the power of 43 times per second. That's a 1 followed by 43 zeros. No atom, no field, no physical system can oscillate that fast without disintegrating. To probe times that short, you'd have to create energy so high and concentrate them into such a tiny region that the very act of measurement would warp spacetime itself. This is where the problem becomes catastrophic. According to Heisenberg's uncertainty principle, the smaller the region, or shorter the time you try to observe, the higher the energy required to do so. You can think of it as sharpening your focus. The more precisely you want to see, the more energy your light must have. At the Planck scale, that required energy density becomes so immense that it exceeds what gravity can handle. The region you're trying to observe collapses into a black hole. In other words, to look closely enough to see a Planck moment is to destroy the very space-time you're trying to measure. It's the ultimate paradox of observation. Nature doesn't just hide the Planck scale, it protects it. Let's imagine for a moment what such an experiment would entail. Suppose you tried to build a detector capable of resolving intervals shorter than 10 to the power of minus 44 seconds. You'd need to confine an immense amount of energy, roughly equivalent to the Planck energy, which is about 1.95 times 10 to the power of 9 joules. That's roughly the energy of a speeding truck packed into a single subatomic particle. At that density, space-time curvature becomes infinite. A singularity forms. Your experiment wouldn't yield data, it would yield a miniature black hole that evaporates in a flash of Hawking radiation. The very fabric you were trying to probe would fold in on itself. You would have reached a literal limit of measurability, not because your instruments are inadequate, but because the universe itself refuses to cooperate. It's as if reality is saying, you can know this far and no further. So if direct observation is impossible, can we at least infer what happens at the Planck scale indirectly? Physicists have tried, and continue to try, through some of the most ingenious methods imaginable. One approach looks to the heavens, where nature's most extreme experiments are already taking place. Ultra-high-energy cosmic rays, particles that travel across billions of light years, sometimes strike Earth's atmosphere with energies far greater than anything our accelerators can achieve. If Planck-scale effects subtly alter the way particles propagate through space-time, we might detect it in these cosmic messengers. Scientists study the arrival times, energy distributions, and trajectories of these particles, searching for deviations that could hint at space-time's granularity, perhaps a sign that light doesn't move perfectly smoothly through the vacuum, but experiences minute fluctuations caused by quantum foam. So far, observations haven't shown any conclusive evidence. If space-time has a grainy structure, its influence must be incredibly faint, smaller even than we can currently detect. Another window may come from gravitational waves, the ripples in space-time first detected in 2015. When two black holes merge, they release bursts of gravitational energy that travel across the cosmos, stretching and compressing the fabric of space as they go. Some physicists speculate that if space-time truly is quantum at its core, these waves might interact with that granularity, leaving faint echoes or distortions in the signal. By examining the patterns of these waves with exquisite precision, we might catch a whisper of Planck-scale physics, a vibration left over from the smallest units of time. Experiments like LIGO and Virgo have begun pushing the limits of what's measurable. Their instruments can detect changes in length smaller than 1,000th the diameter of a proton. But to sense the Planck scale, they would need to be roughly 20 orders of magnitude more sensitive, a gulf so vast that for now it's beyond even our dreams. Still, the universe offers us clues. When black holes evaporate, when the cosmos expands, when energy and gravity meet, something must govern the physics at that boundary. Even if we can't see it directly, its effects ripple upward into the observable world, just as we infer the existence of atoms or dark matter without ever touching them. Yet there's a growing realization among physicists and philosophers alike that some things might remain forever beyond observation, not because they're hidden, but because they define the very stage on which observation occurs. Planck time may be one of those things. To measure it would require a clock smaller than the fabric of time itself, operating faster than causality allows. It's not just impractical, it's conceptually meaningless. You can't build a ruler to measure the atoms of the ruler. It's as though reality has drawn a final boundary. A smallest possible moment. A quantum of existence beneath which there is no before and after. This doesn't make it unimportant. It makes it profound, because in physics, knowing where knowledge ends is itself a kind of wisdom. Planck time stands as a reminder that the universe, however vast or intricate, contains limits not only of scale, but of meaning. Beyond that limit, our equations, our instruments, even our language fail. Perhaps this is not a wall to be broken, but a horizon, a point beyond which curiosity must become contemplation. To know that there are things forever beyond reach is not defeat, it's humility. It tells us that existence itself still holds secrets, not because we haven't looked hard enough, but because the act of looking is part of the mystery. And so, even if we never measure Planck time, we can still measure its significance, as the line between what can be known and what must be imagined. It's the smallest moment the universe allows. The instant where the measurable ends and the unknowable begins. A boundary not only in physics, but in wonder itself. The closer we look at time, the less it behaves like what we think it is. It slips between definitions, sometimes a flowing river, sometimes a ticking clock, sometimes a mirage that exists only because we're here to see it. The Planck time, the smallest possible interval, raises a question that isn't just scientific, but profoundly philosophical. Is time continuous, unfolding smoothly like silk, or is it quantized, made of indivisible moments, like pearls on an invisible thread? If it's continuous, then between any two moments there's always another, an infinity of instants packed into every second. But if it's quantized, then time itself has atoms. Smallest possible ticks that reality can experience, indivisible and absolute. Between one tick and the next, nothing can happen, because between does not exist. It's an unsettling thought that even time might be pixelated. The ancient Greeks already sensed this strangeness. The philosopher Zeno of Elea, writing in the 5th century BCE, composed a series of paradoxes to expose the contradictions hidden in motion and continuity. His most famous one is Achilles and the tortoise. In it, the swift hero Achilles gives a tortoise a head start in a race. Zeno argued that Achilles can never catch the tortoise, because before reaching the tortoise, he must reach the halfway point, and before that, half of that distance, and before that, half again, endlessly. An infinite number of steps, each smaller than the last. Mathematically, we know that the infinite series of halves converges, that Achilles does in fact catch up, but Zeno's deeper point still lingers. If time and space are truly continuous, then motion requires crossing an infinite number of divisions. How can anything happen if it must complete an infinity of tasks in a finite time? Perhaps Zeno was suggesting continuity is an illusion. Modern physics gives that old puzzle a new dimension. If time really is built from discrete Planck-sized quanta, then Zeno's paradox dissolves. Achilles doesn't have to cross infinite halves. He crosses a finite number of Planck lengths in a finite number of Planck times. Reality becomes computable. The film of existence advances frame by frame. But if that's true, then what lies between those frames? Do we exist in the gaps, or only in the frames themselves? Do things happen continuously, or do they update, like a simulation refreshing its display one instant at a time? Quantum physics adds another twist. In the quantum world, events don't unfold continuously. They occur through quantum jumps, abrupt transitions between states. An electron doesn't slide gradually from one orbit to another. It disappears from one and reappears in another, as if skipping a beat. At larger scales, those jumps blur into smooth motion. But at the foundation, the universe seems to work in snapshots. The Planck moment may be the smallest of these snapshots, the cosmic shutter speed of reality. If that's the case, then the flow of time is not a property of the universe, but a sensation created by our limited perception, our inability to see the gaps between frames. It's like listening to music. Each note is discrete, but when played fast enough, it becomes melody. Perhaps the universe is doing the same, playing existence fast enough for it to feel like continuity. Some physicists think this smoothness might be an illusion arising from something even deeper: entanglement. In quantum mechanics, entanglement is the strange connection between particles that share the same quantum state. Even if separated by light years, they remain linked. A change in one is reflected instantly in the other. Einstein called it spooky action at a distance, but modern physics has revealed something even spookier. Spacetime itself might be built from these entangled relationships. According to the ER equals EPR idea, proposed by physicists Juan Maldacena and Leonard Susskind, every entangled pair of particles is connected by a tiny wormhole called an Einstein-Rosen bridge. In other words, entanglement and spacetime geometry might be two sides of the same coin. If that's true, then time, the unfolding of events, could be a byproduct of the way information is shared between these entangled connections. Time would not exist as an independent backdrop, but as an emergent property of correlation itself. When things become entangled, they form relationships. When those relationships evolve, we experience that evolution as the passage of time. This paints a staggering picture. The universe might not have started in time. It might have created time. The Planck moment, that unimaginably brief tick, could be the smallest meaningful update in a vast quantum network, a fundamental pulse in the computation of existence. Reality might be less like a river and more like a heartbeat. And just as consciousness arises from the combined activity of countless neurons, the flow of time might arise from the collective activity of countless quantum interactions. The ticking of the universe may be the sound of relationships changing, but if time is emergent, not fundamental, what does that mean for the way we live inside it? If the present is built moment by moment, does the future already exist, waiting to unfold? Or does it come into being only when observed, only when information is exchanged, only when the universe, or perhaps consciousness itself, notices? This question cuts directly into one of the oldest human debates: free will versus determinism. If time is continuous and all its moments already exist, like pages in a book, then the future is as real as the past. We merely move through it, reading the story that's already written. In that view, free will is an illusion. Every choice is predetermined by the state of the previous frame. But if time is discrete and emergent, if each moment crystallizes only when the universe computes it, then the future truly isn't fixed. It doesn't exist until it's made. Our actions, our choices, become part of how the next moment forms. That doesn't make us omnipotent. It simply means the story is being written as it's read. Reality, then, is participatory. We are not passengers through time. We are co-authors of its unfolding. Our perception of now may be another illusion born from this process. Neuroscience tells us that what we experience as the present is a construction, a kind of mental average of the past few hundred milliseconds. Your brain stitches together sensory inputs that don't actually arrive at the same time. By the time you feel this moment, it's already gone. So even within our consciousness, now is not instantaneous. It's assembled. We experience time as smooth because our brains, like the universe itself, fill in the gaps. Perhaps then, the Planck time is more than a number. It's a metaphor for awareness. It represents the smallest possible difference between before and after. the atomic unit of change. Everything that happens, from the birth of a star to the firing of a neuron, is made of countless of these moments stacked together. We live our lives unaware of them, just as fish live unaware of the water. Yet every heartbeat, every thought, every second of experience is made from an endless chain of Planck moments, linking what was to what will be. Between those moments, in that infinitesimal pause where time might not yet exist, lies the mystery of what it means to be. And maybe that's the real wonder of Planck Time. It shows us that even the smallest instant contains the whole story of existence, that the entire universe and all its unfolding fits between two ticks of the smallest clock that can ever be. Somewhere between eternity and an instant, that's where humanity lives. Suspended between the infinite and the infinitesimal, between the ages of galaxies and the smallest tick that the universe will allow, every moment of your life unfolds in that vast in-between. To the universe, it's nothing more than a shimmer, a faint ripple on an endless sea of time. And yet, to you, that ripple feels like everything. It's strange, isn't it? We can measure the age of stars, the distance to galaxies, the half-life of atoms, and still, when faced with the smallest possible moment, we stand silent. We can name it. 5.39 times 10 to the power of minus 44 seconds. But we can never touch it, never feel it, never live inside it. It's the universe's whisper, just below the threshold of perception. To even speak of Planck Time is to stand at the edge of meaning. It marks a horizon where physics fades into poetry, where equations give way to awe. Beyond it, we can't describe the world with words or mathematics, only with wonder. If you could somehow slow the universe to its ultimate rhythm, you'd find it beating to a tempo beyond hearing. Each pulse, one Planck moment, would be the shortest drumbeat imaginable, the smallest fragment of now. Yet, within those pulses, the whole story of existence is written. Every breath you take, every star that burns, every life that begins and ends, all unfold across an unimaginable number of these tiny intervals. The universe, in its grandest scale, is built from whispers of time so faint that reality itself seems to hum between them. There's a deep humility in realizing how small we are against that scale, and yet how vast our thoughts can reach. We may never observe a Planck moment, but we can imagine it. We can calculate its value, describe its consequences, and feel its mystery. And perhaps that's what makes our species extraordinary. We don't just live inside the flow of time. We reflect upon it. We build clocks to measure it, theories to explain it, and stories to make peace with it. We stretch our minds across billions of years, and then shrink them down to 10 to the power of minus 44 seconds. And both scales feel equally real in our imagination. That ability to see ourselves between those two infinities may be the most human thing we possess. The Planck instant is unreachable not because it's far away, but because it's too close, too fundamental. It is the frame rate of existence itself, the baseline rhythm of reality. You are already living within it, built from it, made of it. Every second of your consciousness is a tapestry woven from Planck-sized threads. When you move your hand, countless trillions of Planck moments pass. When you close your eyes, the universe advances through uncountable instants that make up a single breath. And when you sleep, the clock of existence keeps ticking, silently, invisibly, at the only tempo the cosmos has ever known. You are not separate from that clock. You are it, observing itself. Maybe that's what time truly is. The universe looking at itself changing. Each instant a reflection of what just was, becoming what will be. And in between those reflections, in the invisible gap between before and after, lies everything we can't yet understand. We often think of time as something that passes, something that moves around us. But perhaps it's the opposite. Perhaps time doesn't pass at all. We do. We drift through it like waves through the ocean, tracing temporary patterns across an eternal sea. And when those patterns fade, the sea remains, still vibrating with the same Planck-sized rhythm, still waiting to give birth to something new. The more we learn about the smallest moment, the more it reminds us that understanding has limits. And those limits aren't failures, they're invitations. They remind us that curiosity itself is part of the design, that the universe has left room for wonder. Every great discovery begins at such a limit. Einstein found one at the edge of light, Planck found one at the edge of the infinitesimal. And somewhere at the next horizon, someone else will find another, not by breaking the boundaries, but by listening to what they say. For the smallest tick of time speaks quietly but clearly, that existence itself has structure, that even nothingness has texture, that beneath all our equations there is music, the music of limits, of proportion, of things that cannot be smaller or faster or simpler than they are. It's a song we can never hear directly, yet every atom dances to its rhythm. So here we are, standing at the edge of time, gazing both forward and backward. Behind us lies the history of the cosmos. Billions of years of expansion, of stars, of life. Ahead of us lies what we can never see, the realm below the Planck moment, where meaning itself dissolves. Between the two is the narrow bridge we call now. That's where you stand. That's where you live. Not in the infinite, not in the infinitesimal, but in the miracle of awareness that connects them. Take a moment right now to feel it. The steady rhythm of your breath. The faint pulse in your fingertips. Each beat is an echo of cosmic time. Ancient, patient, and endless. You are part of the universe's self-measurement, its awareness made visible, and though you may never experience a single Planck moment, you exist because of them. They are the dust of time itself, the silent gears that keep the universe turning. To know that, even faintly, is to stand in quiet awe, not of something distant, but of the fact that you are here, conscious, at this precise intersection of space and time. So let this thought settle. Let it slow you down. You don't need to chase time or measure it. You're already made of it. The smallest moment and the longest eternity are not opposites. They are reflections of the same truth. They meet inside you. And as the sound of the world softens, as your mind begins to wander through the vast and the minute, remember, the universe never stops ticking, but you don't need to keep up. You only need to listen. For in the quiet between two Planck moments, between two heartbeats, lies everything that ever was and everything that will ever be. Rest there for a while, let the mystery breathe, and let yourself drift, timeless, in the silence at the edge of time.